Hello everyone and welcome to our channel Mootechie. It's a pleasure to have you here, whether you're a student diving into material science, an engineer brushing up on fundamentals, or just curious about how we make metals stronger and more durable. Today we're exploring a foundational topic in metallurgy, the heat treatment process. So let's get started and unlock the secrets of transforming metal properties. Now let's begin our journey into the world of heat treatment. We start with the A3 line on our diagram, which helps us understand the structural changes in steel. This includes the A1 line, which marks the eutectoid temperature, a key point where a single solid phase transforms into two other solid phases upon cooling. We also have the hypoeutectoid region for steels with less carbon than the eutectoid composition, and the hypereutectoid region for steels with more carbon than the eutectoid composition. Moving on, let's look at the iron-carbon binary phase diagram, which shows us the temperature regions for a process called full annealing. The vertical axis is temperature in degrees Celsius, and the horizontal axis is carbon percentage ranging from 0 to 2.2%. The diagram shows different regions. At high temperatures we have austenite, also known as gamma iron. There's a line called ACM, and regions like austenite plus cementite and austenite plus ferrite. The area marked for full annealing sits within these regions. Below that we have the A1 line. At lower temperatures, we find ferrite or alpha iron, and regions like ferrite plus pearlite and cementite plus pearlite. This diagram is our essential map for understanding how heat and carbon content change steel's internal structure. Next, we see a diagram illustrating different cooling paths for austenite. If we use slow cooling Z-Pro, we get a structure called pearlite, sometimes with a pre-eutectoid phase. With moderate cooling, we get a finer structure known as Bainite. And if we use a rapid quench, we get a very hard and brittle structure called Martensite. The speed of cooling is truly the magic wand that shapes the final properties of the steel. Now let's dive into the introduction. Steel and other alloys have a huge number of applications in engineering practice under varying conditions, requiring many different properties from them. They might be required to bear static or dynamic loads, revolve at extremely high speeds, operate in highly corrosive media, carry an extremely hard skin with a tough core, or be subjected to fatigue and creep. But sometimes, a material may lack some or all of these properties, either fully or partially. This is where the incredible process of heat treatment comes in, to fulfill these deficiencies. Generally, all steels can be heat treated as needed. And interestingly, aluminum is the only non-ferrous metal that can be effectively heat treated. So what exactly is heat treatment? The process involves heating solid metals to specified recrystallization temperatures, holding them at that temperature and then cooling them at suitable rates. This is all done to enable the metals to acquire the desired properties to the required extents. All heat treatment processes therefore comprise three key stages. First, heating the metal to a predefined temperature. Second, holding it at that temperature for sufficient time so that the structure of the metal becomes uniform throughout. And third, cooling the metal at a predetermined rate in a suitable media. This forces the metal to acquire a desired internal structure and thus obtain the desired properties. All this happens because of changes in the size, form, nature, and the distribution of different constituents in the microstructure of these metals. What is the purpose of all this? Let's explore. 1. To relieve internal stresses set up during other operations like casting, welding, or hot and cold working. 2. To improve mechanical properties like hardness, toughness, strength, and ductility. 3. To improve machinability. 4. To change the internal structure to improve resistance to heat, wear, and corrosion. 5. To effect a change in their grain size. 6. To soften them, making them suitable for operations like cold rolling and wire drawing. 7. To improve their electrical and magnetic properties. 8. To make their structure homogeneous and remove coring and segregation. And 9. To drive out trapped gases. As you can see, heat treatment is a versatile tool for a materials engineer. Now let's look at the classification of heat treatment processes. The main processes are 1. Annealing, 2. Normalizing, 3. Hardening, 4. Tempering, and 5. Case hardening, which is also known as surface hardening or diffusion coating. The diagram here simply contrasts the general outcomes, annealed metals versus hardened metals. Annealing is one of the most important heat treatment processes. The internal structure of the metal gets stabilized through this process. Different types of annealing processes can be classified as follows. 1. Full annealing. 2. Process annealing. 3. Spheroidized annealing. 4. Diffusion annealing. And 5. Isothermal annealing. A chart on this slide shows the temperature ranges for these processes against carbon content. For hypoeutectoid steels, we have the normalizing range and the hardening or annealing range in the ferrite plus pearlite region. For hypereutectoid steels, we see the spheroidizing range in the pearlite plus cementite region. So why do we anneal? It's to achieve one or more of the following objectives. 1. To refine the grains and provide a homogeneous structure. 2. To relieve internal stresses set up during earlier operations. 3. To soften the metal and thus improve its machinability. 4. To effect changes in some mechanical, electrical, and magnetic properties. 5. To prepare steel for further treatment or processing. 6. To drive out gases trapped during casting. And 7. To produce a desired macrostructure. Let's discuss the first type, full annealing. The diagram illustrates the stages: heating, holding at the critical temperature, and then transforming during cooling. In full annealing, also called high-temperature annealing, the main objectives are to soften the metal, relieve its stresses, and refine its grain structure. In this process, complete phase recrystallization takes place, which means all imperfections of the previous structure are wiped out. This involves heating steel to a temperature about 30 to 50 degrees above the higher critical point for hypoeutectoid steels, and by the same amount above the lower critical point for hypereutectoid steels. We hold it at that temperature for sufficient time to allow internal changes to take place and then cool it slowly. The steel gets softened by this process, together with an appreciable amount of increase in its ductility and toughness. Here is a handy table for annealing temperatures for carbon steels. Steel type: carbon percentage, annealing temperature degree C, dead mild steel, less than 0.15%, 870 to 930, mild steel, 0.15 to 0.3%, 840 to 870, medium carbon steel, 0.3 to 0.8%, 760 to 840, high carbon steel, 0.8 to 1.5%, 760 to 780. Now what about the cooling process in high temperature annealing? Cooling is done by allowing approximately 3 to 4 minutes per millimeter thickness of the largest section at elevated temperatures. High temperature cooling is usually done in the furnace itself by lowering the temperature at a rate of 10 to 30 degrees Celsius per hour, down below the lower critical temperature. The specimen is then air-cooled down to room temperature. This process makes a coarse pearlitic structure which is quite soft and ductile. An alternate method of cooling after soaking is to embed the metal in a non-conducting material like sand, lime, mica, or ash. Next up is process annealing. It has many names: slow temperature annealing, subcritical annealing, or commercial annealing. The objective is to remove the ill effects of cold working and soften the metal so its ductility is restored. This means it can be plastically deformed again or put into service without danger of fracture. This process is extremely useful for mild steels and low carbon steels. It's cheaper and quicker than full annealing and also produces less scale. The main outputs are increased ductility and plasticity, improved shock resistance, reduced hardness, improved machinability, and removal of internal stresses. During cold working operations like cold rolling or wire drawing, a metal gets severely strain hardened. To fix this, we heat the metal to a temperature between 550 degrees Celsius to 650 degrees Celsius, hold it there for enough time to allow recrystallization, and then cool it at a slower rate, normally in air. Let's explore spheroidized annealing. The main objective here is to produce a structure of steel which consists of globules or well-dispersed spheroids of cementite in a ferrite matrix. There are two main methods to achieve this. For high carbon steels, we heat the steel to a temperature slightly above the lower critical point, say between 730 degrees Celsius to 770 degrees Celsius, hold it, then cool it in the furnace to 600 degrees Celsius to 550 degrees Celsius to 550 degrees Celsius, followed by slow cooling in still air. For tool steels and high alloy steels, we heat to a higher temperature of 750 degrees Celsius to 800 degrees Celsius or more. Hold it at that temperature for several hours and then cool slowly. Now on to diffusion annealing. The objective is to remove heterogeneity in the chemical composition of steel ingots and heavy castings. This process is mainly used as a preliminary step before applying full annealing to steel castings. Here, the metal is heated to a very high temperature between 1100 degrees Celsius to 1200 degrees Celsius, where diffusion occurs and grains are homogenized. The piece is held at this diffusion temperature for a short time, then cooled down to between 800 degrees Celsius to 850 degrees Celsius by keeping it inside the shut-off furnace for about 6 to 8 hours. After that, it's removed and cooled in air. Finally, full annealing is performed. Another type is isothermal annealing. This consists of heating steel to an austenite state and then cooling it down relatively quickly to a temperature of about 630 degrees Celsius to 680 degrees Celsius. It is followed by holding it at this constant or isothermal temperature for some time and then cooling it down to room temperature at a rapid rate. During the isothermal holding, full decomposition to a pearlite structure takes place, which gives the process its name. Because of the two rapid cooling stages, the total annealing time is considerably reduced, making it more efficient. Let's move forward to normalizing. The normalizing process is similar to annealing in sequence, but differs in the heating temperature range, holding time, and the rate of cooling. The heating temperature of steel is 40 to 50 degrees Celsius above the higher critical point. It's held there for a relatively very short period of time, about 15 minutes, and then cooled down to room temperature in still air. This heat treatment is commonly used as the final treatment for articles that are supposed to be subjected to higher stress during operation. So what are the benefits of normalizing? Due to this treatment, internal stresses from previous operations are removed, loosened, the internal structure is refined to fine grains, and the mechanical properties of the steel are improved. This process also improves the impact strength, yield point, and ultimate tensile strength of steels. Compared to annealed steels of the same composition, normalized steels are less ductile but stronger and harder. So for improvement of mechanical properties, normalizing is preferred. But to attain better machinability, softening, and greater removal of internal stress, annealing is the better choice. Now, let's talk about hardening. This process is widely applied to cutting tools, machine parts made from alloy steels, dies, and heavy-duty components. In hardening, steel is heated to a temperature within the hardening range, that's 30 degrees Celsius to 50 degrees Celsius, above the higher critical point for hypoeutectoid steels, and the same above the lower critical point for hypereutectoid steels. It's held to attain an austenitic structure and then cooled rapidly by quenching in a suitable medium like water, oil, or a salt bath. The diagram on this slide shows the temperature curve over time. It includes the holding period, the rapid quenching step which leads to an as-quenched state, and then a subsequent tempering step which results in a quenched and tempered state with better properties. In hardening, by rapid quenching we disallow transformation at the lower critical point and force it to happen at a much lower temperature. The rapid cooling gives the metal too little time, preventing transformation at the higher temperature and forming a very hard structure. But a hardened steel piece, due to its martensitic structure, is extremely hard and brittle, making it unsuitable for most uses. This brings us to tempering. A subsequent treatment is needed to obtain a desired degree of toughness, at the cost of some strength and hardness, to make it suitable for use, especially for tools. This process enables the transformation of some martensite into ferrite and cementite. The exact amount transformed depends on the reheating temperature and the time allowed. The tempering process involves reheating the hardened steel to a temperature below the lower critical temperature, holding it there for sufficient time and then cooling it slowly to room temperature. If good impact strength is desired, reheating should not extend beyond 300 degrees to 350 degrees Celsius. The thickness of the component also has a decisive effect. Heavier sections require longer tempering times than thinner ones. There are different types of tempering: low temperature tempering, medium temperature tempering, and high temperature tempering. Let's look at low temperature tempering. This treatment reduces internal stresses and improves toughness and ductility without any appreciable loss in hardness. The heating range is from 150 degrees Celsius to 250 degrees Celsius. You might see different colors appearing on the metal surface which are indicative of the approximate temperature it has attained. Carbon tool steels, low alloy tool steels, case carburized parts, surface hardened parts, and measuring tools are often tempered by this method. Next is medium temperature tempering. This involves reheating the component to a temperature between 350 degrees Celsius to 450 degrees Celsius, holding it and then cooling it. This method increases the toughness of steel, but reduces the hardness. It also increases ductility and decreases strength. It's mainly used for articles that need high yield strength coupled with toughness and that are subjected to impact loading, like coils, springs, hammers, and chisels. Finally, high temperature tempering. This process involves reheating the hardened steel to a temperature between 500 degrees Celsius to 650 degrees Celsius, holding it and then cooling it down. This enables the steel to attain high ductility while retaining enough hardness. It provides a useful combination of good strength and toughness, with complete elimination of internal stresses. Examples of its use include crankshafts, connecting rods, and gears. Let's discuss one last category: case hardening, also known as surface hardening or diffusion coating. Case hardening consists of heating a steel in the presence of a solid, liquid, or gas rich in carbon. This enables the surface to be hardened while retaining a tough, ductile core. Examples include carburizing, cyaniding, and nitriding. The diagram shows a simple setup for pack carburizing. A part to be carburized is placed in a sealed steel container with activated charcoal. When heated, the charcoal produces carbon monoxide, which releases carbon atoms to diffuse into the surface of the steel part. And that brings us to our conclusion. Metal is heat treated to give it certain desired properties. Let's recap some key needs and their treatments. To soften the metal, we use annealing. To harden it to resist wear, or to enable it to cut other metals, we use hardening. To remove some of the extreme brittleness caused by hardening, we apply tempering. And to refine the structure after it has been distorted by hammering or cold working, we use normalizing. Thank you for joining this deep dive into the heat treatment of metals. We hope this session has been illuminating and has strengthened your understanding of how we engineer the properties of the materials around us. Thank you. See you in the next class.